Okay. So here we have the next part of lesson 4.4 where they're talking about logarithmic scales, log scales. And the question is, why do we need them? I'm going to play a little game with you to kind of explain why. So what I want you to do is on a piece of your paper, find a clear part of paper and make a line across your paper. Don't make it too small, maybe most of the width of the paper. On one side, I want you to put a 0. And then on the other side, I want you to put 1 billion. So that was 1,000, 1,000,000, 1 billion. Okay, so this is 0 on one side. This is 1 billion on the other side. What I want you to do is make a mark on here, like this is a ruler. Make a mark on your ruler where 1 million lives. So where on this ruler is 1 million? And if anyone is brave enough, put a note in the chat about where I should make my mark. So first you try it, think about it. Seems easy, but it's not obvious at first. And in the chat, you can either just chat or just chat privately to me, but I want to hear from at least one person before I move on. It's right next to 0. Thank you for that, chat. Yeah, let's suppose like I said, let's put it here. Well, if that was 1 billion, then this over here, sorry, 1 million, then 2 million would be over here. But 2 million, I'd have to count up to get to a billion. How far would I have to count? Well, 1 million is that spot right there. So it turns out a billion is 1,000 million. So I need 1,000 equally spaced marks here. And the first one of those is going to be the million. So if there's like a billionaires club and I try to join because I'm a millionaire, I'm pocket change to those guys. Dude, you don't live in our block, sorry. Okay, so this is super important. This is why we need logarithmic scales. What a logarithmic scale does, instead of plotting the actual number, we just keep track of the power. So for a billion, for example, has 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros. So a billion is 10 to the 9th power. A million has 6 zeros, so it's 10 to the 6th power. And the point of a logarithmic scale, a log scale, is instead of plotting the number, you just plot the power. What would that look like? Well, I'm just going to go from 0 out. 1, 2, 3, 4, 5, 6, make believe they're equally spaced, 7, 8, 9, and 10. This is a log scale. Up here, I have a linear scale, two different things. So on a log scale, 1 billion would live right here. 10 to the 9th, I just plot the 9, the power. So on a log scale, that right there is 1 billion. The million is 10 to the 6, so on a logarithmic scale, 1 million lives right here. Why does it live there? Because it is 10 to the power 6, and we only worry about plotting the power, not the whole number. So on a linear scale, this right there is 1 million. 1 million. If that's 0 and this is 1 billion on a linear scale. On a logarithmic scale, that's where they live. Where would 1,000 live on this scale? 1,000 is 10 to the 3rd power. So right here, that would be 1,000 on this scale. 100 is 10 to the 2nd power. So on a log scale, right there would be 100. Why? Because it's 10 to the second power. A 1 would be where 10 lives on this scale. And the 0 isn't really a 0. On a log scale, that's 1, because 1 is 10 to the power 0. So logarithmic scales actually can't deal with the number 0. That's a problem. But it's not a problem we're worried about. Okay, so what's a log scale? It just means plot the power of 10 for the number. What if I didn't know the power of 10? Like somebody said, okay, where does 5,280 live on this scale? Logs are where that comes in, right? On a calculator, if I say, hey, what's the log of 1,000? My calculator is going to say it's 3. So to plot this number on a log scale, I just say, hey, what's its log? Whip out my calculator. Log of 5,280 is 3.7-ish. So here's 3, there's 4. Let's do this one in red, maybe. 3.7 is about here. So 3.7 on this scale is where 5,280 would be plotted on a log scale. So what it does is it allows me to see small and big numbers in the same view. Otherwise, like if somebody says, okay, on this scale up here, graph 1,000. How am I going to fit 1,000 in here if 1,000,000 is so close to 0? They're touching, it looks like, right? So I can't graph 1,000, 1,000,000, and 1,000,000,000 on the same scale and see them if that scale is linear. That's what log scales are about. All right, back to the assignment. So that's what they're pointing out right here. So here, this is a linear scale at the top, and I can see, you know, Jupiter, Saturn, Uranus, and Neptune, they're way out there. And over here, it looks like Mercury, Venus, Earth, and Mars, they're touching each other. Well, that's just because the scale is distorted in a sense. If we zoom in on those guys, we know they're wicked far apart, right? We can't easily get to Mars, otherwise we'd be there. We ain't. We have enough trouble getting to the moon. If we plot these on a logarithmic scale, where we just plot the power of 10, then we can see some separation in there. But remember, that's a distorted scale, and that's okay. That's okay. So logarithmic scale just plots their powers. So I'm just going to double check a couple of these. So this right here is 1.5. This line right here by Venus is a 2. So if I'm going from 1.5 to 2, this must be 1.6, 1.7, 1.8, and 1.9. So this has Mercury here between 1.7 and 1.8, closer to 1.8. So if we go up to Mercury and its value is 58, what's the log of 58? Let's check. Log of 58 is about 1.76. And again, if this is 1.5, 1.6, 1.7, 1.8, yeah, that's about 1.76 there on this scale. So again, logarithmic scale versus linear scale. Graph the power of 10, just the power, the exponent, not the actual number. Okay, so the scale above shows the dwarf planet Pluto. Use the scale to estimate the distance in kilometers from the sun to Pluto. Okay, so what power is Pluto at here? Well, let's guess. So this is 3.5, that's 3.6, 3.7, 3.8. So it's somewhere in between 3.7 and 3.8, not quite in the middle. So 3.7, 3.8, 3.77 maybe. That's the power. So I'm going to write this down in my notes. Help you grasp it in your mind. This is a tough concept. When I first saw it, it kind of blew my mind. Oops, where did my screenshotter go? Screenshotter, where are you? There you are. Okay, so we want to identify Pluto here. And again, 3.5, 3.6, 3.7. So that right there is the power 3.7. This right here is the power 3.8. And so I think Pluto is a little bit past halfway. So I'm going to guess the power is 3.77. That means the actual distance, so that's the power, the actual distance must be 10 to the 3.77. So we ask a calculator about that. Desmos, please, what is 10 to the power 3.77? Desmos says that's about 5,888. Check on these though. These are all millions of miles. So that's 5,808 million miles, but notice, or not miles, kilometers, pay attention, Gary. And notice it says out here, million kilometers. So really all I need here is the 5,888. Double check my calculator. I think that's 3.5, 3.6, 3.7, 3.8, just a little less than 3.8. I guess 3.77. Yeah, 5,888 million kilometers from the sun. How'd I do? Not bad. It'll accept various answers there in that ballpark. Ida is a large asteroid belt approximately 429 million kilometers from the sun. Plot that on the logarithmic scale. Where does Ida go on this scale here? Okay, so that's this scale up here. So let's see, 4,002, I can't read that right. 429, there we go. So looking up here, 429, that's in between Mars and Jupiter. So there's Mars, there's Jupiter. It's got to be somewhere in between there. How do we figure that out? Okay, so let's do it. How do we figure it out? 429. So again, the way the scale works, it's identifying the power of 10. So we want to know what power of 10 is 429. Other way to state that is the question mark equals log of 429. Because what does the log do? The log tells us the power of 10. That's the whole point of log. What power of 10 is it? So let's type that into a calculator. Right, remember I did that earlier when I was playing around with Mercury. Calculator, log 429, and I get about 2.6-ish. How many decimal places do they want? Well, they want us to actually plot it. Okay, so let me just think about that for a second. Remember up here, we were looking, 429 is between Mars and Jupiter. So between Mars and Jupiter, I'm guessing 2.6. Yeah, that's right in between. That seems okay. So now I just got to try and put a point there. So I think the point goes about here-ish. 2.5, 6, 7, 8, 9, 3. Calculator, log of 429 is about 2.6. Yeah, that looks good. So this isn't too picky about where I put my point. Ooh, it was picky. Okay. So what did I do wrong? I guess I could include more decimals, couldn't I, right? When we did, which one? Pluto, yeah, we guessed that with 2 decimal places. Okay, so 2 decimal places, what is that? 6.3. Okay, where would 6.3 be here? 2.6, 2.67, 2.63. It's about there. Oh, that was better. 2 decimal places. I lost a half a point out of 5. No big whoop. All right, so you do your best to plot that point. If you think you're close enough, message me. Next part. Okay, so a long time ago, there was a stock market crash. Recently, there was a stock market crash, big one. So 1928, big stock market crash. Lots of investors killed themselves, committed suicide. It was so bad. 2010 started in kind of 2008. There was a big stock market crash related to the housing market, related to the way our country was processing loans with a lot of bad loan deals. And we had this huge drop. Question: $1,000 today, is that the same as $1,000 in 1928? Answer is no. If I had $1,000 in 1928, I'd be a very rich man. Today, I'm just like, I can't even buy a car with that. In 1928, I could buy probably several cars with that. So in 1928, back in the beginning here, we can't even see the crash. The reason is we're looking at such big numbers today. What if we were to zoom in there? That's one option. The other option is to redraw this in terms of powers. So down here, we have vertically a logarithmic scale, where we're plotting powers of 10 instead of the actual value. So this is what the drop looks like in a linear scale for 2010-ish. And there's a little bitty drop over here in 1928. I can't even see it. If I look on the logarithmic scale, the 2010 drop looks relatively small, but the 1928 drop looks ginormous. Okay, so let's think about why would that be? So to do that, we're going to look at absolute change versus relative change. We reinvestigated that idea when we were talking about the Ebola outbreak recently. All right, so I need some data here, and that would be in this line here. So I'm going to copy this, stick it in my notebook. Where's my notebook? And we're going to look at absolute and relative change and then compare that to this logarithmic scale. So we're going to take this information and we're going to compare 1928 to 2008, or 1929. Okay, so in 1929, the stock market dropped from 380 to 420. So there's two things to consider there. So first, 1929, we're going to look at the absolute change. So ABS change. That means take the 380, subtract the 42, and what do we get when we do that? We get 340, 338. So the absolute change was $338. Relative change or percent change. So relative / percent change. That means take the 338 out of what you started at. So we dropped 338 out of 380. What is that as a percentage or as a decimal? Let's check that on a calculator. 338 divided by 380. 338 divided by 380, and I get about 88.9%, 0.889. So basically, the amount of money you thought you had if all your money was in the stock market went down by 90%, right? So if you had $100 worth of wealth, you now have like $10 worth of wealth. You went from $100 to $10 overnight, or $1,000 to $100 overnight. Big drop. In 2008, the change is from 14,100 down to 7,500. So I want to know what that difference is, and then I want to find that as a percent relative change. So 14,100, 7,500, 14,100 minus 7,500 gives me a drop of $6,600. What is that as a percent of what we started at, the 14,000? So 6,600 divided by 14,100, that's a drop of about 46.8%. So 660, 46.8. So we have an absolute change of $6,600. The percent change is that absolute change divided by the original amount, which ends up being about 46.8%, or as a decimal, 0.468. So in 1929, although the stock market only dropped from 380 to 42, that's a drop of $338. That was actually around a 90% drop in wealth. That's a big drop. In 2008, people lost, if you started with $14,000, you lost $6,000. Now feels like a huge hit, but it's only about 50% of your wealth. What would you rather lose, 50% of your wealth or 90% of your wealth? I'll take the 50% if I have to pick a loss, right? So absolute dollar wise, this looks like a bigger number, but compared to what we started at, the 1929 was a worse deal in terms of percent of one's wealth. And that's what the logarithm shows. The logarithm shows that considering where they started, 1929 was a bigger percent drop in wealth than in 2008. And the next couple of questions go over that. The absolute change, 338, relative change as a percent, what's that one again? 88.9. Absolute versus relative. Get that right? Yep. Okay, so absolute dollars wise, it looks like 2008 was worse. Percent wise, 1929 was way, way worse of a drop. And that's what these next two questions are about. I'll let you answer those two.